Greetings and happy Monday. Let's see.
Good morning.
How's everyone today? Functional? Sweet. Let's see. So you owe me a project or a quiz today. Those of you in my class last term are familiar with this, but quickly, where did you all go? There you are. Quickly, my screen, my open math screen is what I see, not what you see, unless I click on student view. I have a few extra things, obviously, because I'm controlling the class, but just to reiterate, this is what I'm going to do. Actually, when I get out of class today, I'm going to click on this. You don't have this option, but I'm going to click grades. I'm going to go in here and start grading stuff. And so what I should see is this. I should see upload your homework below. And I'm going to click on this. Joseph scanned this in. So you're sending me one PDF file that's got 4 pages or whatever, and send it to me through my open math, because this is where I'm going to grade it. This is where I'm going to find it. I get a lot of emails because of department share and other math classes. And if you send it to my regular email, it's going to be hard to find. So I'm going to grade this. You don't owe it to me until later tonight, but hopefully by 11 o'clock tonight. Joe's is turned in already. Thomas's is turned in already. I wouldn't think yours would be turned in yet unless you're just really on the ball and got it figured out. But I've taught you everything. There's nothing about 5.5 on it. So I'd say you're ahead of the game and doing awesome if you already got it in. But this is where I should see it. So any questions about that? Is that working okay? Anybody have anything weird happen and have any advice for people, something they figured out that wasn't clear on there or whatever? Instrumental music. Okay. All right. I got something awesome to show you today, and it is the first skill that will be on the test that gets you out of difficulty when the problem is not quite so straightforward. You really end up in this class in, as I said before, we had all these kind of rules in derivatives where we had the product rule. So you had to recognize, hey, that's 2 things multiplied. I got to use the product rule. Or, oh, 2 things are divided. I got to use the quotient rule. Or junk inside of junk. That's the chain rule. So you had to recognize certain situations. And this is kind of the same, except fortunately, there's only 2 of those rules. But the downside of it is it's very difficult sometimes to tell which one to use, and I'll try to illustrate that today. And as usual, my goal here is to make you understand the logic of this and the principle behind it. And so I really just want to go slow. And this is an example of a place where, as a teacher, I think we just need to do lots of examples until you kind of get the feel of it. But as always, I definitely want you to interrupt me. So as an example, in previous sections, we said, oh yeah, no problem, I can handle this. So if I gave you this on a test, you should be just fine. Now, that's reminiscent of, and when you see that, you should say, uh-oh, 2 things divided, not good. Because quotient rule was hard with derivatives. And so given that the fundamental theorem of calculus says we're just going backwards, we have to take the antiderivative, some mathematicians say. not the derivative, but the antiderivative or the derivative in reverse. So if you think quotient rule for a fraction was difficult, we got to do that in reverse. But in this case, you can mess with it, right? Algebraically, you can mess with this and get rid of the fraction. You can say, hey, 2x divided by x is 2x. I'm sorry, 2x over x, which cancels to 2. And then 3 over x is 3 over x, or 3x to the negative 1. Maybe you might write it that way. And so, oh, okay, good. Fraction gone. Great. Now I can just use regular old, well, power rule, or again, power rule in reverse. But remember, this is the one tricky thing about power rule. It doesn't matter. This exponent right here can be anything except what it is for us, -1. Anything but -1. Why? Because the reverse of the power rule says add 1 to it and then divide by that number. Well, if you add 1 to -1, you get 0. And then when you proceed to divide by 0, everything kind of blows up to infinity. So that's kind of the one exception to the rule. What do you got to do in that case?
Substitute in ln x.
Yeah. And you might forget that. That's kind of the one reason I'm showing you this really quickly. Like, you might forget that and say, oh, power rule, no problem. But when you add 1 to it and divide, it's like, oh, I'm dividing by 0. That should be kind of a, oh, that's right. That was that one weird exception. So the integral of 2, and remember, that's really x to the 0. If you add 1 to that, it becomes x to the 1 and then divide by 1. So you end up with 2x to the 1 divided by 1. And the integral of 1 over x is natural log of x, and that's a -3. So that just comes along for the ride. Notice I didn't forget the plus c. Notice this was not again, what mathematicians call a definite integral. By the way, if you had a question like that on the test, even if I didn't ask you to come up with an area, you should go back and supply your own. Go back and supply your own limits, because you can check this on Desmos or on your graphing calculator to make sure it's right. Like, I might have made a mistake here, right? Like, I might be wrong about this, but how do I check it? Well, remember, you got to graph it to check it, to make sure you don't choose numbers that don't work. Remember, I played with an example the other day that didn't work. So you might go back and, say, oh, I'll evaluate this from 4 to 2. And then I'll come over here and evaluate this from 4 to 2 and make sure I get the same answer, because I can cheat to get this answer. And then over here, I can plug 4 and 2. And if I get the same answer, then again, I can talk smack on the test and say, you don't even need to check this because I know it's right. So check it. Now, today, starting 5.5, which we're going to spend 2 days on using a technique called substitution, which is a good name for it. You'll see why in a minute. I'm going to take that same exact problem, except flip it over. I just want you to stare at that for a second. Up to now, you've been given problems where you could always get out of it. In other words, it was 2 things multiplied. Well, you could multiply them out, and then they weren't multiplied anymore. So you didn't have the product rule. Or in the last problem, oh, 2 things divided. Well, you were able to divide them and there was no division anymore, no problem. Well, in this case, you can't get out of it. Do you see that algebraically? Hopefully you do not think this is equal to x over 2x minus x over 3. That's not true. If it was, then we would get out of division again and we'd be okay. But that's not true. So we're stuck with it this time. Like, it is division. And so, uh-oh, I can't get out of it. And I'll erase this, but much in the same way, if it's something like x over the sine of x or something, like, you're stuck with that division problem. And so, how am I going to get out of this mess? And fortunately for you, there is no, I don't think I will erase this. There is no quotient rule. Like, as I said, quotient rule forwards was kind of challenging. And so how are we going to go backwards on the quotient rule? There isn't one. And really, that's what's going on here. So substitution, and here's kind of the idea. And this is kind of a silly example, but it's so apropos that I can't not share it. So you might have watched somebody boxing on TV or watched was it UFC, Universal Fight Club? Is that what's called, UFC? But it's like there's some person that is just tougher than you, maybe a bully when you were a kid or whatever, and you can't beat them up because they're bigger than you and so forth. This technique is really about saying, well, you probably can't beat up a UFC fighter, but what if they were only shrunk down to 1 inch tall? Then could you beat them up? Yep, every one of you could, because you could just step on them. And that's kind of what we're going to do here. In other words, this fight, again, it's kind of a stupid illustration, but this fight right here, you're not going to win it. You're not tough enough. I'm not tough enough. But you can switch it out. You can substitute it out for something a lot smaller and easier. And that's the trick of substitution. The problem with substitution is it's not always obvious what to pick for your substitution. And that's why we got to practice a bunch of these. So substitution is, here's a fraction that I can't get rid of. I know quotient rule is hard. I'm in trouble. I'm going to have to make some kind of a substitution. I got to make this an easier problem for myself. I got to make it shrink down. The problem is, what do I pick? That takes a lot of practice to get really good at. And again, I don't think the point in this class is to get really good at this. You're not, 99.9% of you are not going to go in the world and ever need to take an integral like this. That's why I think my job is ultimately to teach you how to think more than anything else. So we don't need to get awesome at this. You're not going to have to do this to build a bridge. Why? Well, I've been showing you, you've got a cheat button. You never do indefinite integrals in the real world. You might do definite integrals where, it's from 5 to 2, but remember, you can just cheat for that. Have your calculator tell you what the answer is and get on with it. You don't actually have to know the integral. It's only true mathematicians. So I think this is worth our time. We want to get reasonable at it, but we don't have to get awesome at it. Let me show you the idea then. Here it is. So before we sort of didn't mind if there was just a single X down there, but when there's a plus sign down there because of distributive law or a minus sign, that's not so good anymore. And so we really wish that wasn't there. That's kind of the idea. Dang, man, I wish that was just an X or something like that. Well, then let's do that. And I think I'm going to come back here before no, I'll come back and do that later. Let's let u be equal to 2x minus 3. So what I'm really doing is introducing a brand new letter to this that really isn't there. Sweet. So if that's true, then wouldn't it now be that? Do you see why I picked that? Like, that wasn't so hard a second ago, was it? I don't mind if there's only one thing down there, just a u or an x. I didn't mind that. And so, well, then let's put one there. Now, what's the problem with doing that? You tell me, like, reason this out. Go slow here. Why is that problematic?
How do we take the antiderivative of u?
Well, if that's 1 over u, isn't it natural log of u?
Well, then aren't we getting the derivative, like the antiderivative with respect to this u or something?
Yeah. In other words, that u is just like any other letter. Like, the integral of x is x squared over 2. The integral of u is u squared over 2. It's just some other letter. You had some problems that had t's in them and things. It doesn't really matter what the letter is, so I don't care if it's a u.
Well, but didn't we want it like with respect to x probably with the lesson?
Yeah, now that does muddy the waters a little bit, but does it make sense we still have an x here and an x here? Like, we can't just pretend those are gone. And we can't, really what it comes down to is, if we're going to switch to u for a letter, then we got to switch everything to u. We got to have u's everywhere. We got to have du, not dx. We got to have no x's. You can't just stick the x and the dx in there and say, okay, great, go. Like, it's got to be all u's now. And so you're committed to finish this process that you started. I just did the easy part. Hey, I wish that was a u on the bottom, or again, I can't say x because I already used x. Any other letter you want to pick, w, who cares? V. Great, but the problem is I got to keep going. So how are you going to get rid of this x up here?
Could you say it's like 3/2 u or whatever the algebra works out to?
Yeah, Exactly. Like, don't we have an expression now since we let u be equal to, that's our really our only connection between these two universes, if you will. So if that's what u is equal to, then couldn't you just solve that for x? So Felix is on it. So if I add 3 to both sides, then I'd have u plus 3 equals 2x. And then if I divided by 2, I'd have u plus 3 divided by 2 equals x. So I got rid of that. Now, this is why substitution's hard. Does it make sense? You could potentially substitute it into something worse. Again, to follow the idiotic illustration I was using, if you think you can't beat a UFC fighter, what if they grew to 20 feet tall? You substituted the wrong direction and it's even worse. You're going to do that a lot because you're kind of just wading into this. But the thing you got to be comfortable with is just try. Like, you can actually get every one of these problems right. Don't see this as a maze. There's only one way through it and you have to choose the right thing the first time. Just succeed in substituting it into a totally different letter and then reevaluate and say, is this easier for me? If the answer is no, then say, well, I guess I should have substituted something else. Can I come up with some other idea? That was a terrible idea. I'm also going to show you how to check to see if you didn't screw up. So cool. Actually, I know that x could actually be rewritten as u plus 3 over 2, or 1/2 u plus 3 halves, or whatever, however you want to write it. I'll just write it as it is right now. What are you going to do with that dx? How are you going to get dx gone? From Math 251, where did dx's come from? How do you get them? If all you have, this is kind of our connection, as I said, between the two worlds. That's the only thing I know that tells me how u and x are related to each other. But how do I turn that into dx's and du's? That's not hard from 251. What do I do?
Can't you just put dx over du, because isn't that taking the derivative? Because didn't we put dx over dy and that was like the derivative? But in this case, it's our x value.
That's exactly right. Like, just take its derivative. Isn't that how you create? I mean, if that's an equation that relates u's and x's, can't you just take its derivative? And if you do that, don't you get du's and dx's? And so now you made a new equation. I mean, this equation right here allowed you to switch this into an equation with it solved for x instead of u. So if we create an equation with du's and dx's in it, then couldn't we solve it for dx and then replace that dx? Now, there's a couple of ways to do that. One would be to kind of do what Eve said, which is to say, well, like before, if this was a y, didn't we say the answer to that was dy dx equals, and the derivative of 2x minus 3 is just 2? Isn't that what we did? So wouldn't this be kind of no different? It'd just be du over dx equals 2. I think you might find it easier, though, to maybe look at it this way. Like, just think of it as taking the derivative of both sides, because that's more algebraic. In other words, I look at the left side and I say, hey, there's u sitting over there. What's the derivative of u? Well, it's the derivative of u times 1, I guess. And then you look to the other side and you say, okay, what's the derivative of 2x? Well, the derivative of 2x is 2. And the derivative of 2x is 2 times dx. 2 times the derivative of x, just like the derivative of u is du. It's not 1 because we don't know what kind of world we're in. If I was taking the derivative of u with respect to u, it'd be 1, but the derivative of u is just u prime. Maybe you remember from, what was that called? Implicit differentiation. What's the derivative of y? And we said it was y prime because we don't know what it is. Same here. What's the derivative of u? U prime, du. What's the derivative of 2x? 2 times the derivative of x. What's the derivative of 3? 0. I'm probably going to use the second method more than the first, but first of all, do you agree those are the same answer? However you kind of choose to think about it. Well, if I resolve this for dx, then doesn't this say if I just divide by 2, isn't that du over 2? So basically, that's too dark. So basically, I have an expression for x in terms of u that I can also replace. And now I have an expression with dx that I can also replace. So what do I finally have? I've completely changed this into another letter now. So let's see how it worked. So I have the integral of u on the bottom. X is replaced with u plus 3 over 2. And dx is replaced with du over 2. Now you see fractions everywhere, and so that might initially look intimidating, but this is now doable. Like you just switch this into something that you can now solve. Let's play with it for just a minute. Let's see here. Hopefully your algebra skills are such that this is really easy to you. Let's see, there's a 2 there, and there's another 2 here. So that's 4. And remember, you can always pull that out front. Remember how constants went along for the ride, like the derivative of 6x squared. The derivative of x squared is 2x, and the 6 was just there along for the ride. And same thing's here. Since there's a 4 on the bottom, maybe I'll just take it out front. And so now I have u plus 3 over u. Are you seeing now that, oh yeah, I can do this. I can now do this problem. Because there's only one thing, and that's one of the things you want to look for is when you see 2 terms on the bottom like this, generally it's a good substitution to let u be whatever is on the bottom of that thing. Like there could be a parabola down there, like x squared plus 6x minus 9. Well, then let u be the whole thing. Because I'm not troubled by one term on the bottom, but I'm troubled by 2 terms, 2x and a 3. I'm troubled by that. That doesn't work so good. I'm stuck.
Could you explain a little bit of this algebra that just happened?
Yeah, what did I do? I just looked at this mess here, and I'm glad you asked. Like, slow down and ask me algebra questions. I see that, this is just kind of like a big fraction. Since this is u plus 3 over 2, I kind of thought of it as, well, what if I multiply the top by 2 and I multiply the bottom by 2 so that those cancel? So that's why the 2 went to the bottom. So now because I don't want fractions over the top of fractions. So I ended up with u plus 3 over 2u. And then I also had this 2 out here. So because you multiply fractions straight across, that 2 just got multiplied over here with the other one. So it became a 4. Did I say enough about that, Felix?
Yeah, that makes sense.
Thank you for asking. Please ask all those questions. If nothing else, it just gives people time to soak because I'm talking too fast.
I have a quick question.
Go ahead.
In the
Really loud. Can't hear you very well. Go ahead.
Sorry. In the dx du part, where did you get the 2 from?
From this expression here. So when I said, hey, let's take the derivative of u, that's u prime. The derivative of u is u prime. What's the derivative of 2 times x? Well, remember the 2 just comes along for the ride. What's the derivative of x? It's x prime. And then what's the derivative of 3? Nothing. I'm just writing u prime as du and x prime is dx. So the 2 is just there because when you take derivatives, it just comes along for the ride. And then when I solve for dx, I just divided that 2 over to the other side. So let's stare at something. Let me just show you something really quick while you're thinking about this. So this is our original problem right here. x over 2x minus 3. Now I'd like to, as I said before, I'd like to kind of cheat and put some limits of integration here, like actually make this a definite integral just to kind of check and see if this is actually working. Because I got it down to here and I'm sort of wondering, I'm sort of kind of sitting here going, is that right? Like we did just do a whole bunch of algebra and a whole bunch of derivative taking and moving things around, and I very easily could have done something wrong here, but I did get it entirely into a different world, right? I was in X world and now I'm in U world, and you should be a little bothered by the fact that, you know, like there's no such thing as U in this problem, and how are you going to get back? Because remember, your victory over the UFC fighter is not very glorious if they just lay on the ground dead an inch tall. After they're laying there dead, then they got to grow back to their full size, and then you're glorious, right? Because you beat this 6 footer or whatever. So we got to get back into X's before we're all finished. But I'm not sure I've even got this right. So I'm going to go to Desmos, x over 2x minus 3. And what did we say before? I think I told you can type integral. I'm going to try that right now and see if I was telling you the truth. Yeah, you type the word integral and it throws that up there. And I have no idea what numbers to choose because I haven't really thought about it. So I'm just going to throw a couple numbers in there, like, I don't know, 1 and 4. And our problem was x over 2x minus 3. I guess I don't need that, do I? Backspace x divided by, no, I don't need that either because it gave me the division sign. 2x minus 3. Go. How come it's not going? I said this the other day. Why isn't it working?
You forgot your dx, or
yeah, it doesn't like it if you don't show the width of the rectangle. How come it says undefined? I don't know.
Is it because the function isn't defined at those limits of integration?
Exactly. Remember how there's places where graphs are weird. And when you have fractions, don't you have kind of asymptotes? And so I just accidentally, and I truly mean accidentally, I just chose something that didn't make sense. It's always a good idea to go in here and say, I would like to graph the equation x divided by 2x minus 3. It's always a good idea to graph that first so you know what it looks like. Do you see why it didn't work now? Again, I did that entirely by accident, but notice there's a discontinuity, a mathematician would say. There's a hole in the graph. Well, of course there is, right at 1.5, right? Because if you, on the bottom of that fraction, if you put 1.5 in for x, 2 times 1.5 is 3, minus 3 is 0. It breaks, it explodes. So my limit of integration went from 4 to 1. So it included that gap in the graph. That was dumb. If I graphed it first, I might have said, hey, look, the graph looks a lot better from like 2 to 4, doesn't it? Like 2 to 4 would be fine. So then I could go back up here and sort of fix that. But without this graph, I didn't really know that. So now it's fine. So the one thing about Desmos that's not as cool as your graphing calculator is notice it doesn't show me the area that I'm taking the integral of. The other thing that's kind of cool is if you do take the trouble to graph this first, I wonder, can I go up here and just say the integral of, I'm pretty sure the answer to this is yes. Can I just say the integral of f of x then? Since I already defined f of x down below. So now I see the graph. And so I made 2 to 4 up. Do you understand that? Just to kind of make sure that I know what I'm talking about. And let's see. I don't know if there is in Desmos a way to kind of shade that. I wish there was. But you understand this. If I go from 2 to 4, you can see it sitting there. Let's see, do I have the ability to trace? Not really. I think I'll draw this out. I'll probably copy this and put it over on my other screen in just a minute.
Sometimes
but you can see that area from 2 to 4. Go ahead.
I was gonna say sometimes what I do is I just do like x equals 2 and then x equals 4 to block off that area.
Yeah.
Let myself see what's going on.
That's exactly right. In other words, that's a good idea. So if you say x equals 2, that's a vertical line. And if you say x equals 4, then it's the area between those. Does that make sense? That's a good idea, Cheyenne, just at least to help visualize it a little bit. So what I'm wondering is, back in this other land over here, I'm wondering, will that give me the exact same answer? Now that I know it's from 4 to 2, will that give me the exact same answer? And maybe I'll, just so it's a little easier to type, maybe I'll throw the 4 back in here. It doesn't really hurt. Doesn't really matter where it is. X plus 3 over 4, I'm sorry, U plus 3 over 4U.
What just happened there? The 4? You put the 4 back in?
Yeah, instead of having it outside, I just thought because I'm lazy, I'll type it back into the inside. So let's see, on the top, it was U plus 3. And actually, I don't know. Could I just do this with U? Maybe I should just try. Do I really? I don't know if it's going to like the letter U. I'm not sure if it sees that as a variable. I don't know my alphabet. I can't even find U.
It's by Y.
It only took me 20 minutes. Oh, cool. So it didn't mind that I used U. Uh-oh. That's not good. You understand that? Can you see that the area under the blue graph is not the area, the same as the area under the black graph?
Wouldn't you have to change your limits of integration into terms of U?
What do
Were
you?
you using ones from the first time you did it, were you using X, you were using X's?
What do you think about what Alicia said? She's questioning the 4 and the 2. And back here, when I plugged in 4 and 2, isn't that x equals 4 and x equals 2? Like those are x's too, aren't they? If we're going to switch worlds, can they just still be 4 and 2? No. How do you switch them?
Would you put, when you did your U equals for the substitution, would you put those into that equation to get the U? If you did some algebra to move it around?
That's exactly right.
Or would you just put it straight in?
Isn't that connection right there? That's the connection between the two worlds. If U is equal to 2x minus 3, doesn't that convert our x's into u's? So if I stick a 4 in here, 2 times 4 is 8 minus 3 is 5. So a 4 in X land is a 5 in U land. So what's a 2? 2 times 2 is 4. 4 minus 3 is 1. Now does it work? Let's go find out. So this is saying, yeah, the black graph and the blue graph are not the same graph, but it is saying that the areas will be the same. You just have to go from 5 to 1, not 4 to 2. So down here then, if I say integral from 1 to 5, and now I get to type just GU because I already have that typed in. And I guess I would have to say then du. Did it work? Worked. That's the essence. Now, Do you notice? Do you notice that from 2 to 4, that's a different shaped graph, and it's sort of narrower and taller, right? Whereas when we switch to the other one, it's wider and shorter, but we actually still got the same area. So the thing is, you're getting the same numerical area, but it's not like it looks the same. You're not getting that exact same shape you see right there. You're getting a totally different shape. So just to give you time to soak on that a little bit. Let's see, does that give us everything? That gives us everything. This can be bigger. It's almost amazing that this works, I guess, is kind of what I'm getting at.
Sorry to be going back to this. I'm just not really sure where that 4U, like you kind of like just put the 4 in there or something. I'm not really aware of what happened there.
Yeah, that's because back here, I multiplied the top and the bottom by 2, so these would cancel. And so there was a 2 down here then. And then there was still a 2 over here. And so 2 times 2 is 4. But
yeah, that makes
sense.
I
thought, oh, let's just put it outside. But then I thought, yeah, that's true, but I don't want to write it out there. I don't want to write 1/4 times the integral of something. Thanks for.
Yeah, I have no idea how I missed that. It was just early morning and it wasn't written as a 4, so I was confused.
I got no problem with that. As I said, when you ask those questions, it just gives people time to process a little bit because I'm talking too fast and we just need to think a little bit. We have time. So everybody is agreeing that what we are essentially trying to find is that area right there, right? And as I said before, do you need calculus to find this area? Well, apparently not, because I just cheated and found it, right? So the real world, that's what I'm going to do. So just so that you're visualizing this carefully, then let's go back to this screen, turn those off, turn this one on. And I guess in the interest of time, I'll just go back and change these from 1 to 5. So we're saying that's the same exact area. Do you see what I'm saying? So it's way wider and way shorter. Isn't that interesting?
Yeah, it's just interesting because if you were looking at it in terms of like time and something else, it's like kind of totally different, but it equals the same area.
Yeah. So the thing is, I guess when I was first learning this, I was thinking that somehow what you're doing is getting the exact same shape somewhere. No, you're not getting the exact same shape. You're getting the same area, but you're getting it in a kind of, if you will, kind of a totally different way. Ooh, almost lost the 5 there.
I think what you're saying, Justin, is like you have like your original parameters from the original equation. So if you did have like a time that was like 2 to 4 seconds or something, you would figure out the area and then go back to those original parameters.
Yeah. So do you see the logic in this? We're taking something that in x's we can't do. You can't take the integral the way it was before. There is no such thing as the reverse of the quotient rule. Remember how complicated that was? How are you supposed to go backwards in that? You can't. So what you're doing by substitution is just changing it into something a little easier for yourself. But you just got to be algebraically extremely careful. Did you see how easy it is to lose 2's? And like, you got to switch everything. You got to look at the original problem and say, you sort of got to look at this and say, there's an x, there's an x, there's an x. If I'm going to switch this, I got to have all those turn into u's. And do you see how important it was to not ignore the dx? Remember how kind of we were just ignoring it, we weren't really using it for anything? But here, that dx got substituted into du over 2. Like our answer would have been 2 times too big, so to speak. We would have got, instead of 2.2, we would have got 4.4 if we'd have just said, oh, just switch du and dx. No, those don't matter. No, they do matter. You got to switch every one of them, and you got to do it algebraically, and you got to do it slowly. Let me review, and I'll show you a really good problem in just a second, but just as a quick other example, you had a problem in your assignment that wasn't e to the x, it was like e to the 5x. And I purposely put that in there. Really, this is a substitution problem, but you would have had to get this right kind of just based on logic. In other words, I know the derivative of e to the 5x. I know the derivative of e to the 5x is e to the 5x. The derivative of e to the junk is e to the junk. But what else, because of chain rule, what also do you have to do?
It's 5e to the 5x, right?
Yeah, times the derivative of the junk. The junk is 5x and the derivative of that is 5. And so what would the integral, maybe I'll switch to another number just so you don't really see these as kind of the same question, but what would the integral then? I got to go backwards. And again, what I'm trying to do is as I sort of know the answer to this is e to the 4x, because the derivative of e to the 4x is e to the 4x. So the integral would be also e to the 4x. But what you have to think of is the integral goes this way. Well, if I took the derivative of e to the 4x, kind of this answer over here, I don't get that. What else do I get? Well, there's a times 4 there, right? In other words, I'd be multiplying by 4. So in a sense, you might say this would be true. If there was a 4 there, it would have worked.
Yeah, so the integral has to be divided by 4 in order for the 4's to cancel out.
That's exactly right. And so it's kind of reversed. Like in a derivative, you multiplied. Well, here you'd divide. So if I took the derivative of e to the 4x, wouldn't it be e to the 4x times 4? And then the 4's would cancel. And so you can get that based on logic, and you might have survived that in the assignment. But a better way to look at this, or a more systematic way to look at it, and again, notice I was kind of lazy in the way that I wrote that down, and I will stop being so lazy now because it needs the dx there, right? Is to substitute. So there's 2 things you don't like to see. One of them is in the denominator of the fraction, you don't want to see x plus 7. You don't want to see 3x minus 9. You don't want to see 2 terms down there. You also don't want to see functions inside of functions. Like this 4x is inside of e. That's a chain rule. You don't want to see the square root of the sine of x. That's sine of x, which is its own problem, but then it's inside a square root. I don't want to see stuff like that because that's like chain rule. And how do I go backwards in the chain rule? And you got to be really careful about that. And so the systematic way to do this, or the brainless way to do it, rather than sitting there guessing, thinking, am I multiplying by 4, dividing by 4? I'm confused, is to do what we've been doing today, which is to say, well, I'll pick a different letter this time. I'll let w equal that 4x. That way the problem just becomes e to the w. Okay, great. The integral of e to the w is e to the w. Am I done though? The answer is no. I still have this dx to get rid of. How do I get dx's? Well, this is your converter, if you will. So if I take the derivative of w to get dw's and dx's, I've got to take the derivative. Again, I'll write it this way this time. The derivative of w is the derivative of w. 4 comes along for the ride. The derivative of x is the derivative of x. So dw is 4 dx. So, okay, that means dx is equal to dw over 4. So this isn't just ignore it, it's dw over 4. And again, the 1/4, I can just sort of ignore it. I mean, I could write it as 1/4. And then it just comes along for the ride. The integral of e to the w is e to the w. Now, the one thing we didn't finish in the last problem that we're going to go back and finish right now is like this problem never had W's in it. Are we done now? No, there was never any W's in this problem. What do we have to do to finish it?
Let W
Switch
equal
it back.
Yeah, just put it back. In other words, wasn't W equal to 4x? So technically there'd be plus C in this problem. And so there, now I'm done. There never was a W. You won. The W is just there to keep you from getting confused.
Why is it plus C?
Because there could be a plus 7 there. Remember what you're saying is if you take the derivative of this, if you take the derivative of that, you'll get your e to the 4x back again. That's the fundamental theorem of calculus. Integrals are hard. So if you get all done and you think, am I right? You could cheat like I showed you and graph it, but you could also take the derivative of 1/4 e to the 4x and see if you get e to the 4x back, and notice you do. Why is there a plus C there, technically?
Because there could be any number there that if you took the derivative of, it would go away.
Couldn't be said any better than that. If that was a plus 9, when you take the derivative of 9, doesn't it go away? So that's just, it's just pointing out to people that, hey, there could be actually hundreds of answers to this. Any constant you want to put there, and that's why it's a C. C for constant. You can't put a letter there. That's not good because derivative of letters are not 0, but you can put any constant you want there. Again, for what you know right now, that just, it feels like a technicality. Technically, it should be there. You might get something wrong on my labs or my open math. On the if I give you a question like this on a test, I'm going to sit there and have to struggle like, do I take a point off or something like that because they forgot to throw the plus C in there. My tendency is to probably say, who cares? I mean, I probably write it on there, but technically that's the right answer to this. Well, so let's go back here then and actually finish this question since we now know the answer to it. And mostly because I forgot. So couldn't you now say, if I go up here, since I can actually divide them, don't I have U over 4U, the U's cancel and I just get 1/4. And then I have 3 over 4U, which is, I'm going to write it as 3/4 times 1 over U. Maybe you understand why I'm writing it like that. Du. Remember there was never a 5 and a 1 there or a 4 and a 2. I just threw those in to check my work. And now I can take the integral with respect to U. The integral of 1/4, it grows a constant, U. The integral of 1 over U, that's natural log of U. And the 3/4 just comes along for the ride. That's the reason I wrote it that way. If I write it as 3 over 4U, it's harder for me to see that. Anytime I see 1 over U or 1 over X, oh, the integral of that's natural log. And so since U was 2x minus 3, then isn't my final answer 1/4 times 2x minus 3? Put my U back, plus 3/4 times the natural log of 2x minus 3. And again, technically plus C. Now, wait a second. You're telling me the integral of x over 2x minus 3 looks like that huge answer I just got? I almost can't believe that. Can you? Does that bother you at all? That equals this answer we just got.
I mean, we did kind of take a lot out of it while we were substituting, because that whole bottom term we set equal to the one u. So it looked nice when it was written with u, but now that you replace u with the 2x minus 3, it looks a lot worse.
Yeah, I mean and I'm sort of not kidding when I, like, before it kind of looked like it was okay, and now all of a sudden I'm thinking, really? How do I check this? I mean, I have two things I could do. I could put the 4 and the 1 back in. Does it make sense? I'm sorry, what was it? 4 and 2. I could put the 4 and 2 back in, and I could evaluate this answer over here at 4 and 2 and see if they produce the same area, right? I know the area is 2.2, and so I could plug that in. I could check that, but let's do it a little more sophisticated way. What's the most sophisticated way I could do this? I'm asking you to read my mind, obviously, but.
Take the derivative?
Exactly. Fundamental theorem of calculus says if the blue is the integral of the green, then that means if I take the derivative of the blue, I'll get my green back again, right? So, And notice I'm taking the derivative with respect to x. So the derivative of 1/4, and I almost have to kind of multiply this in so I don't screw it up. 1/4 times 2 is a half. This is a half x minus 3/4. So the derivative of a half x is a half. I find myself looking at that green answer going, that's not going to work. And then the derivative of 3/4 is nothing. And then the 3/4 comes along for the ride. What's the derivative of natural log of junk?
1 over the junk.
1 over the junk. And we're not quite done because what does chain rule say?
Multiplied by the junk.
Multiplied by the derivative of the junk, right? The derivative of 2x minus 3 is 2.
Yeah, my mistake.
That's what you meant. Just clarifying. And notice, hey, there is a 2x minus 3 in the bottom like there was in the green problem. And so that's a good sign. And so let's see. But I've also got that half out there. That seems really confusing. So that half seems very damaging. And then I got a bunch of fractions to multiply. So I have a 2 times 3 on the top, which is 6. And I have a 4 times 2x minus 3 on the bottom, which I could multiply in and get 8x minus 12. But since I'm trying to get it to look like, doesn't look like it worked to me. What do you think?
Maybe. We just need to clean that up.
I like it. Don't give up too quickly. I'm not sure yet. This cancels to 3 and this cancels to 2. Can you add 1/2 and that other expression? How do you add fractions? So they already have a 2 in common, but if I multiplied the 1/2 top and bottom by 2x minus 3, then wouldn't they have a common denominator? So if I did that, on top I have a 2x minus 3 plus 3, which just becomes 2x. And on the bottom I have 2 times 2x minus 3. Look at that. I did get my answer back again. Sure enough. And remember, I was sort of a little bit lazy. I just left the plus c off. I mean, I could have wrote plus c, but then the derivative of that would have been nothing, and so it wouldn't have been there, right? So now I know I got it right. But isn't it weird? Like it looked really strange. It's hard to believe that's actually the right answer. Can you see that you never would have guessed it? Can you see that, like if you just stare at this without all the substitution, how are you going to get that green fraction to suddenly turn into the giant disaster that it turned into? Like there's not a way. You're not winning this fight. This is you versus UFC. You're going to have to substitute. You're going to have to make it smaller. You're going to have to do something different. But it's amazing that it actually works. So you sort of got to trust the process. And you got to really be careful algebraically to substitute everything out.
I have a question.
Yeah.
On tests, are you going to want us to always go back to like X's if we do substitution? Or are you going to tell us like if you want it to go back to X's or?
Yeah, that's a great question. If the problem started out as an indefinite integral, meaning that 2 and the 4 weren't there, then you got to put the X's back because there never was any U's in this. And if you put U's there, it's like, what the heck are you talking about? This isn't even in the universe. But if there was a 4 and a 2 there, meaning a definite integral, and you succeed in getting this into U's, then you can just evaluate it with U's and put in 5 and 1 and get your numerical answer, and then you're done. Does that make sense? And for the most part on tests, I'm going to put numbers there. And the reason I'm going to do that is just to save you the trouble of having to make them up for yourself and to sort of force you to check it. If I put numbers there, I mean, it actually saves you a little time if I don't, because then you don't actually have to plug anything in. But it sort of forces you to do what you should be doing anyway, which is checking your work and making sure it all kind of matches. Because you can cheat and get the right answer. If it's a definite integral with numbers, you can cheat and get the right answer in 2 seconds. And then you just proceed with your math and see if you can produce the same thing using your calculus and algebra skills. And if you can't, then you know, hey, something's wrong, and you can write me a note. It's a good question. Okay, so let's try this example. Can you do that right now? Would you agree that you could do that right now without substitution? Why could you do that before today?
You could multiply it out into a polynomial.
Yeah, multiply that x minus 3 out and then distribute the 4x out. And then you got junk plus junk plus junk. They're all powers, and you could just use the power rule and you're done. If you were given this problem, that'd be the easiest thing to do if you notice that. But if this is a square root, does it make sense you can't multiply 4x inside there? Because and I'd be willing to bet most of you couldn't answer why not. Why can't I just multiply the 4x in there and then take the square root? Why is that algebraically not okay? It's not just because, do you know the answer to that, or do you just kind of know when you can't really explain why? It's pretty simple. It's just sort of operations. Do you multiply first, or do you do exponents first? Square root's an exponent.
Well, isn't it 4x times the square root?
Yep.
If you could just times it, wouldn't it be in the square root?
If the only way you could multiply it together is if the 4x was also in a square root. But if you distribute this in here, then you are doing multiplication before exponents, because x minus 3, maybe it's easier to see if I write it like this, x minus 3 is raised to the 1/2 power. And so if you multiply before exponents, you just screwed up the order of operations and you just broke it, like it isn't true. Now, if that was true, then maybe we could make progress. But my point is, you're stuck here. What I'm staring at is, well, kind of like the alter ego of the product rule, junk times junk. And you're not going to be able to do it. You can't go backwards. And the product rule is kind of, there's a lot of steps to it. And so how am I supposed to undo all of that? You can't. So you're going to have to make some kind of a substitution here to make it something you can do. Would you be able to do this? This is very similar to what I showed you a second ago. Would you be able to do this if that 3 wasn't there?
Yeah, then it's 4x times x to the 1/2, and you can add the exponents together, right?
Nice job, Bill. Because now there is not a distributive law problem, not a plus sign. And so 4x times x to the 1/2, that'd be 4x to the 3/2. And now you don't have product rule anymore. Do you see what I'm saying? It just went away. Now you can just do power rule. Add 1 to that. That'd be x to the 5/2 and divide by 5/2. You're on your way. No problem. So it's like the subtlest things. If you don't understand your algebra really well, the subtlest things, like you're stuck with this. You're not getting rid of that multiplication sign that's right out there. So you're stuck. Now, what I just showed you is the key to one of your possible substitutions. What if you let u be equal to that x minus 3 inside there so that it was just the square root of u? Does that make sense? Maybe that would work then. Or maybe I should let u be the whole square root. Like, let's get rid of the whole thing. Do those both work? Is one of them better than the other? The answer is, I don't know. Like, try it. The key to this concept is you look at something you can't solve and you change it into something else. You might change it into something that's worse than it was before. Maybe both of these would work, and one of them is easier than the other. One is a 1-inch midget and the other is a 2-inch one. I can win both of those, if you will. I don't know. Let's try. Let's just try it. If you want to understand this stuff, you got to see this as kind of fun. Like rather than, oh no, what do I do? Somebody tell me what to do. Like, just try stuff. So I'm going to try this. Let's just see what happens. Remember, not only, I mean, that's going to make short work of, this. But remember, you still have that and that to get rid of. So how am I going to do that? Is there a way to do that?
Yeah, you can find out what x is in relation to u.
Yeah. Just resolve this. So if I add 3 to both sides, wouldn't u plus 3 be equal to x? Cool. Just got rid of that. How are you going to get rid of dx? Remember, that's just the only way I get du's and dx's into the world is just taking derivatives. And so if I take the derivative of that statement, the derivative of u is the derivative of u, the derivative of x is the derivative of x, and the derivative of 3 is nothing. That's kind of cool. In this case, notice it said they're kind of interchangeable. Since there wasn't a number in front of the x, it's like du and dx are the same thing. Cool. All right, I got everything then. So that means the 4 is still there. The x is now replaced with u plus 3. And I have the square root of u, and I have du. Mission accomplished. But now you got to reevaluate. Is that doable? Like, is that any better? Is it worse? Can I do that now? Unless someone is telling you what substitution to make, that is not an obvious answer. When you get it switched over, you'll just have to see. Remember, I said you can check this. We could go back to the original graph. I'm going to erase this, but I could say from like 4 to 1 and maybe down here that's 7 to 2 and kind of make sure they both get the same decimal answers just to make sure I didn't screw up. Okay, good. It worked. I didn't blow it. I know this is true. Well,
So would our limitations be like x being less than 3? because it would make it a negative number under the square root.
Nice job. Like what I just stuck up there a second ago. Justin just pointed out, once again, that's not going to work because when you put 1 into the square root of x minus 3, you're going to get a negative number. So does it make sense I'd have to, so, you know, think about it a little bit. Don't just throw numbers in like I did. Maybe if you put in like 4 minus 3 is 1, and then let's see, I'd like another perfect square, 12. 12 minus 3 is 9, and the square root of 9 is 3. Like maybe that'd make my life really easy. But let's check this in the fastest way possible this time. So let's I don't think I screwed this up, but what's the answer to my question? Can I do this one? You should be able to tell me that. Maybe you're not sure, but what's your thought? What do you think? Yes, I can. No, I can't.
I would think that you could.
What do you see that, because notice it's still junk times junk. It's like still the product rule. Why do you think you can do it?
You could do u, the square root of u would be like u to the 1/2. And couldn't you just multiply it all out?
Yeah, can't you just distribute that into the parenthesis? Sure you can. So let's see, that'd be 4. There's a 4 out front. U to the 1 times u to the 1/2 would be u to the 3/2 because you add exponents. And then 3 times u to the 1/2 is 3 times u to the 1/2. And then maybe because I could either pull the 4 out in front and just kind of worry about it later, or I could distribute it inside. It's kind of up to you. For this time, I think I'm going to put it inside with everything else because I don't want it to look like product rule. Does that make sense? Isn't that just power rule now? We love plus signs. We do not like multiplication signs. We do not like division signs. Hey, look, I just got rid of all the multiplication signs. Now it's not impossible. You can't do multiplication signs. That's what it comes down to. This substitution is going to work. Okay, let's see. That'd be 4 times u. I add 1 to 3/2. 3/2 plus 2/2 is 5/2. But then I got to divide by 5/2. Add 1 to 1/2. 1/2 plus 2/2 is 3/2. Then I got to divide by 3/2. Let's see, I'm dividing by a fraction, so that'd be the same as multiplying by the reciprocal, so that'd be 8/5 u to the 5/2. And 2/3 times 12 would be 24/3, which is, I guess, a whole number 8. Notice the integral's done, like don't have an integral sign sitting here. You took the integral, that's why it's gone. The integral's gone because I took it. So that red answer is basically my answer. All I have to do now is put I go back here to my converter, my world converter. U is equal to, I already forgot, x minus 3. So my final answer then is 8/5 times x minus 3 to the 5/2 plus 8 times x minus 3 to the 3/2. And again, because I didn't make up a definite integral, again, I don't know about you, but looking back at the original problem, the blue problem at the top up there, isn't it hard to believe that if I took the derivative of that red statement, it was that complicated? If I take the derivative of that red statement, which has a plus sign in it, I'm somehow going to get 4x times the square root of x minus 3. Do you see how you'd never get this any other way? Like you can't guess your way to this. It's just too crazy. So to give you time to process, I'm going to check my work now. I'm going to go to, so I picked 12 to 4. because I think that's going to be a little bit nice on myself. And our problem was, let's see, goodbye, 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 goodbye. Our problem was 4x times the square root of x minus 3. Whoa, huge area, 595. What? This is why sometimes it's good if you're going to check your work, it's maybe good to graph it first before you choose. Like maybe 12 to 4 is too big, but I don't really care. I'm just checking to see if I got a number. What is the graph of, why don't you turn on? There you go. Oh, no wonder. Notice I kind of changed the window. See how tall the Y's are? I kind of stretched it. So when you stick 12 into that, you get a number that's like 120 or something. So no wonder the area is so big, right? Does that make sense? Again, I'd like to see it shaded. So kind of a cool graph. So now when I look back at it, I think maybe a better thing to say would be, well, let's try to let's make our life really easy here. Can you see why I'm picking? Can you see why I picked that? Does it make sense 3 is okay to pick? Because if I put 3 in, does it make sense I'm gonna have 0, the square root of 0? So that seems a lot more sane. It doesn't matter. But I'm just wondering if that's gonna make my life easier when I actually plug it in. So you do this ahead of me. Because that's kind of no joke. That one of the problems with this is that just typing that red equation into your calculator is crazy enough that you could actually screw that up. And you could actually have the problem right, but think you got it wrong just because plugging it in is such a complicated business. So we cheated to discover that area, notice it says it's equal 9.6. That almost kind of makes me think the answer is perfect. It's not rounded off. It wasn't a decimal that kept on going as though I had to round it off. Seems to imply it's exactly equal to that. Isn't that weird? So if I check this then by evaluating this at 4 and at 3, what's that little 2 mean right down there?
It means it's a square root.
Square root. So notice I'm taking the square root of, because it's x minus 3, I'll be taking the square root of 1 and the square root of 0. That's going to make my life really easy. So it's a good thing I didn't just choose like 7 or something like that. I'm actually going to be able, I am going to get an exact answer here because I'm taking the square root and I'm going to get perfect answers for this. So let's see, I got 8/5 times 4 minus 3 is 1. The square root of 1 is 1. 1 to the 5th is 1. So that's just 1. Plus 8 times 4 minus 3 again is 1. That's just 8. And notice it's plus some constant c. And now I proceed to, well, subtraction. Minus 8/5 times, what happens when I put 3 in? 3 minus 3 is 0, and the square root of 0 is 0. So this just goes away. And the same thing happens with 8. The c is still there though. So what happens when I subtract? Notice C minus C is gone. That's why it doesn't matter that it's there. C minus C is gone, and all I have left is 8/5 plus 8. Hey, 8/5 plus 8, 9.6. Cool. Oh, I got it right. 8/5 is 1.6 plus 8 is 9.6. So that didn't take me that long, and now I know I got it right. I must not have blown it because I got the same area. Just for the fun of it, quickly, remember I got to here, and since we're kind of out of time anyway before we start another problem, remember that u was equal to x minus 3, and I chose to go from x equals 4 to x equals 3. So if I put 4 into there, 4 minus 3 is 1, 3 minus 3 is 0. Would you agree that's the same exact answer then? That should also be 9.6. So I'm just going to go to the Desmos and graph that and see, is that also 9.6? And we already know it's going to be because I just checked it a second ago. But the reason I'm doing this is because maybe the graph will look totally different. It's not going to be the same graph, but the area will still be the same. So I'm never going to remember that, so I just wrote it down. So let's see. I'll go find the button this time. Miscellaneous. There's the integral symbol from 0 to 1. And I wish I hadn't erased the other one. Integral of G. Remember, I could type the whole thing. I just kind of like the way this looks. The reason I want this is because I also want to see the graph. Notice it says I can't answer it because you haven't told me what G is. Well, our G of X equation was 4 times, and we saw that we could get away with using the letter U, so I guess I'll just use it. 4 times parentheses, everything in other words, U raised to the 3/2. I think in the interest of saving my precious brain space, I'm going to say 1.5 for that. And then it was plus 3U to the 1/2, but I do have a square root button, so I think I'll just say U for that. Notice I put G of X at the start, not G of U, so it didn't like that. Hey, look, 9.6. What does the graph look like? Notice, interestingly, I'd say those are the same graph this time, wouldn't you? If you look on the green graph from 0 to 1 and on the blue graph from 3 to 4, isn't that exactly the same graph, or at least close? I don't think it actually is the same. Can you tell that on the blue graph there's like a sharper turn? It's like slightly different, but it's not as dissimilar as I would have thought as the last one was.
I think it's the same. It's crossing all the same lines on the y-axis.
Yeah, maybe it is. Maybe it is the same. You're right. When you kind of compare it, looking at the spots, it actually looks the same.
I guess it makes sense when you think about how the only thing difficult about it is the shift 3 to the right.
Nice job. Good observation. This particular substitution we made, U equals X plus 3. Does it make sense that's the shift to the right 3? That's what we just saw, the exact same graph. And so in a sense, I want to say as a mathematician, teaching this as long as I have, actually shouldn't have been surprised it was that. I'm going to start off with this tomorrow. But I want you to try something on your own. I don't know the answer to this question. I wonder if that would work too. I mean, that sure seems nice, right? Like I would have 4x times just u now. Like no square root. Hey, let's get rid of that too. That caused me a lot of problems, didn't it? Gone.
Doug, something that's confusing me is when you're graphing at the end, why is your definite integral coordinates different from the original equation? Like, why is it from 0 to 1 instead of from 3 to 4?
Good job. Who wants to take a stab at that? It's okay to be wrong.
That's because of we changed it into terms of u, and so you have to change those numbers into terms of u. Correct?
Yeah, in other words, this wasn't just 4 and 3, it was x equals 4 and x equals 3. In other words, because
Oh, that's weird. Okay, that makes sense.
yeah, because we were working with x's, those are x's, and so those have to get transformed too. So it's actually down here I highlighted in yellow that we had to also switch out the x and the dx, but if you have limits of integration, you got to switch those out too. Now in our problem, we only introduced those limits of integration just to check our work. So we were sort of technically done right here with this red answer. What do you think? Do you think that's going to work? I'm just asking you before, and I'd like you to get off, and I want to do it right now, but it's going to take me. No, it's not. Let's do it. It's only going to take a couple minutes. Let's do it. Let's see. Well, okay, that took care of that.
Are you going to have to make a second substitution?
Yeah, maybe you're gonna have to make a step. Like this might not work. I don't know. It just seems like another good choice. That's all I'm saying. How are you gonna get rid of that x right there that I just highlighted?
You have to solve the equation for x from the u substitution.
Exactly right. Like that cloud is the only thing you know. That's the connection between the two worlds. Well, can't you still solve that for x? So if I squared both sides, that'd be u squared equals x minus 3. And finally, u squared plus 3 would be equal to x. Still can solve it, can I? Can't I take the derivative to get the dx? Can't I take the derivative? So this time I'm going to write it this way. The derivative of u is the derivative of u. Since this is really x minus 3 to the 1/2 power, do you see that as a chain rule problem? So outer function is the 1/2 comes down front, the junk inside stays unchanged. I subtract 1 from the, and notice you're going to get confused because now we're doing the derivative forward, right? Like some problems are doing it backward when we take the integral. But I'm trying to come up with a derivative for this. Times the derivative of what's inside. What's the derivative of x minus 3?
1.
It's not 1, it's x prime. In other words, we don't know what we're taking the derivative with respect to, at least the way I'm writing it. Now, if you decided I'm going to say du dx over here. In other words, I'm choosing to take the derivative with respect to x, then fine, it is 1. Notice those are the same answer though. Because if I multiplied this dx over to this side, wouldn't it look exactly like the first one? Aha. Then dx is equal to du divided by all that other junk on the other side. That's not good though, because that has an x in it. Do you agree with that? So that's not good. I can't just replace dx and think I'm all done. Is this good or bad? What's happening here? Well, how's
Well,
your
that
algebra skills? Go ahead.
I was just gonna say that 1/2, that's another square root, so you've still got an x minus 3 under a square root, right?
That's exactly right. And notice it's to the negative 1/2 though. And back here, I know what u is as a square root, a positive square root, but how do I get rid of that negative? Which algebra skills? How do I make that not be negative?
You have to put it under 1.
Yeah, we've got to move it. Remember, stuff can move from the top to the bottom and change the sign of the exponent. In other words, if I move that to the top, doesn't it become a positive 1/2, which is in effect, I didn't look up to see who said that, but putting it over 1, you're really dividing by it. Or you could think of it as just multiply the top and the bottom by x minus 3 to the positive 1/2. If you wanted to. Don't you add these exponents? And so now it's x minus 3 to the 0 power and it's gone. So now I can actually just write that as u. Cool. So now what I replace out for dx doesn't have any x's in it anymore. So for a second there, I was thinking, yep, this isn't going to work. But then I didn't give up too soon. Maybe it will actually work. So I don't care about the 4. The x is now replaced with u squared plus 3. The u is there, and then dx is replaced with du over 2, and there's also a u up there. So again, you know, alone, I'm not sure that I didn't make an algebra mistake here, but I did. I did succeed. It's all used now. I got it into a different world. And of course, I'm inclined to want to check it. Does that make sense? It'd be nice to check this, to go back and put 4 and 3 in again and see if I did that here. Let's see if x is 4. Notice I'm taking the square root this time. 4 minus 3 is 1. The square root of 1 is still 1. And 3 minus 3 is 0, and the square root of 3 is still 0. So it's a little bit of a coincidence, but that should still, if I just type that in something, that should still be 9.6. If it is, then that means I really was successful. But the question is, can I actually take the integral of that? Like, is that any easier? Does it even work? Notice it doesn't have any square roots. Frankly, I'm thinking this is awesome. Let's multiply it all together. Let's see, I've got a u and a u to multiply in. And then there's a 4 and a 2. So 4 and 2, 4 divided by 2, that 2's on the bottom. So that's just a 2. And this out here is really a u squared. So when I multiply it in, that becomes u to the 4th. And u squared times 3 is u squared times 3. Did I blow that? Is that okay? Wow. That actually looks easy. That's even easier than the other one. The other one had fractions in it. This looks super easy. I can't even believe this is really working. Let's see, u to the 4th would become u to the 5th divided by 5. And u squared would grow to u to the 3rd, and I divide by 3, but 6 divided by 3 is 2. That sure doesn't look the same as that red answer. I must have got it wrong. What's your thoughts?
Probably not. I mean, you probably just got it in a different form or whatever.
The key is not necessarily like don't give up too soon. This is what happened before. Why might it still work?
Haven't resubstituted the square root of x minus 3 or whatever.
Yeah, remember that u was equal to the square root of x minus 3. So if I plug that back in, then I guess I have 2 times the square root of x minus 3 to the 5th over 5 plus 2 times the square root of x minus 3 to the 3rd. Can you see the connection now? I feel pretty good about everything except for the constants. Isn't the square root of, isn't this statement right here the same thing as x minus 3 to the 5th, but then the square root is 1/2? Isn't that true? Hey, that's looking good. The same thing happens here. I have x minus 3 to the 3rd power, but then also square rooted. So wouldn't that be 3/2? Hey, that's looking good. The only thing that isn't looking good to me is this is 2/5. And this is 2. It's kind of like it's like I lost a 4 somewhere. Did I lose a 4 somewhere? I genuinely think I made a mistake. I can see it's going to work, but I think I made some kind of a math mistake, like I lost something, or just checking my work back here. This was du over 2, and there was a 4, and that 2 got 1/2 got multiplied by 4. That became a 2, so I didn't lose that. Divide by 5, raise 1, divide by 5. Or did I lose a 4? Somebody save us. Four times x was u squared plus 3. Times u times dx. dx was du 2 over 2. Well, I'll fix it in the notes. I kept you guys way too long. I should have followed my own instincts and said, figure it out yourself and we'll do it tomorrow. But someplace I lost a 4 apparently. I just don't see where it is.
When I did my changing the dx to du, I didn't divide it by 2. I multiplied by 2.
That would fix it. I divided by 2 and should have multiplied by 2. Let's see if that's the problem. Oh, yeah, I made a dumb mistake. Everybody see it right here? What's that say? That's a 1/2 on the bottom in the denominator, right? It's not a 2 in the denominator. That's what I wrote here. I wrote a 2 in the denominator. It's a 1/2. Everybody see that? Dividing by 1/2 is multiplying by 2. That 2 should have been up on top. That was a mistake. So that should have been there, meaning this is an 8. Not 4 divided by 2, but 4 times 2. So that'd be 8 times that, and 8 times this is actually 24. So you have 8/5, and 24 divided by 3, this is an 8.
So in doing this math, I've talked to some people and they said integral calculus is one of the harder calculuses. Is this because you can get so lost in this algebra? Like you spent what, 20 minutes doing this just to find out you're wrong because of
Something stupid. I
yeah.
mean, and the other part of it is you can see that there were 2 choices for substitution here and they both worked. Now that's good actually, because it means you pick anything you want and it kind of worked. But you can actually pick a substitution that makes it worse. When I said here, hey, you succeeded, you got it all in to use. That doesn't necessarily mean you got it to a place that's actually going to work. So you can actually spend all these 20 minutes and it's not even any easier, like it's worse in terms of actually taking the integral. So there's a lot of guess and check in this. With derivatives, we already had a method. It's like, oh, look, multiplication. Okay, product rule. There's always a way to do it. Here, you got to try a substitution and just see if it works. And sometimes the substitutions are just brilliant. Like who would ever have thought of that? So yeah, anyway. Yeah, so it's like that kind of, that's why you check your work. Because again, you could tell, I think, that I didn't do that on purpose. And yet, isn't my mistake sort of an understandable one? Like that's the kind of thing I would take a while to check on your test. And I would write something like, dude, and I would circle this and circle this. And then you would look at it just like I did and went, oh yeah, I understand. It's not that I didn't know it, but you're gonna, like I just made that mistake, you're going to, right? So, but again, that doesn't mean I don't understand calculus. I mean, you're still going to get 9 out of 10 on this problem if you don't check your work, because you did all the calculus, right? You just made an algebra mistake. So yeah, I mean, this is going to exacerbate any kind of algebra problems you have for sure. So they both worked. And in some respects, I'd say the second one was actually easier just because it didn't have the square roots in it. Like it just put them in there at the end. But the point of this is not to find the easiest way. You're never going to know that. The key is just be very systematic about substituting. So anyway, I need to shut up. We're going to go practice this more tomorrow. But you know a lot right now. Stay after or I'll see you tomorrow. Sorry I went so long.
Thank you.
Thank you. Thanks for coming.
I had a question about the Excel part of the quiz. And I know we went over